Okay, just doing a sound check to see if I can wear my microphone like this. And guess I'll go and take a listen. Okay, I guess the sound check worked okay. I have to find the angle that maybe gives me the most flattering view. We'll try that. I am really excited. I got Mrs. Rodriguez's new Wacom pen, so I think I'm going to have a lot more control on the pen end of things with my recordings, which is really a blessing because it sure looked like a kindergartner was writing when I was using my other one. So today we're going to talk about stoichiometry. And stoichiometry sounds kind of scary, but it's really not. So to start off with stoichiometry, in class I talked about a peanut butter and jelly sandwich, making a peanut butter and jelly sandwich as an example. And with that, I'll activate my pen here, except I want the pen to be, let's try blue today. With that, I drew a loaf of bread. Oh, this new pen is nice. And I'll try to get it in the 3 dimensions as best I can. And this is not a treasure chest. It is indeed a loaf of bread. All right, and this loaf of bread, I'm not going to draw all those slices, has 22 slices. And then I drew a container of peanut butter. And this peanut butter has 32 servings. And then I drew a container of jelly. And this jelly has 48 servings. And stoichiometry is all about, with chemical reactions, asking yourself, if you start with a certain number of ingredients or reactants, how much of the product are we going to make? So with 22 slices of bread and 32 servings of peanut butter and 48 servings of jelly, I asked the class how many sandwiches we could make. And everybody vehemently said 11 sandwiches, with the basic understanding that one sandwich has 2 pieces of bread. We're not getting into any triple-decker sorts of sandwiches or anything like that. Even though we have 32 servings of peanut butter and 48 servings of jelly, we're still only going to make 11 sandwiches. So the number of pieces of bread is what limits how many sandwiches can be made. Now, after those sandwiches are made, we have some leftover peanut butter and some leftover jelly. So after all of the bread gets used up, we can't make any more sandwiches. The bread is limiting the number of sandwiches, whereas we have excess amounts of peanut butter and jelly. Now, in a chemical reaction, things happen the same way. Oftentimes you have more than one reactant, and we react to form products. And there gets to be a point where if one of the reactants run out, the reaction just stops, and then you have some extra of the other. The one that runs out is called the limiting reactant. The one that still has some remaining behind is called the excess reactant. So stoichiometry is all about figuring out, if you have a certain amount of stuff, how much stuff are you going to make? We have 22 slices of bread and 32 servings of peanut butter and 48 servings of jelly. How many sandwiches are we going to make? So those are the types of questions that we ask. Now, this was just another very similar question. If we want to look at what we have here, we have 8 wheels, 4 frames, and 3 pedal assemblies. How many bicycles can be assembled from the parts shown? I'm not sure what those bouncing dots are on the top of the screen, but if we have 8 wheels, we could construct 4 bikes. If we have 4 frames, we could construct 4 bikes. If we have 3 pedal assemblies, we can construct 3 bikes. And the limiting part in this case is the number of pedal assemblies. So what's controlling the number of bikes that can be made is the pedal assemblies. This would be the limiting reactant. And here we have some extra things left over. We've got 2 wheels and a bike frame. So since stoichiometry involves chemical reactions, and the reactions get used up in this process, if more than one reactant is present, they can be distinguished by a limiting reactant, and then there'll be one or more excess reactants. So the limiting reactant is the one that runs out first. It will limit the amount of product that forms, like the 22 slices of bread making 11 sandwiches, or the 3 bike pedal assemblies making 3 bikes. And the reaction is going to stop when it runs out. We can't make any more product if one of the ingredients runs out. The excess reactant, there will be some left unreacted after the reaction stops. Now, if we are making a product and using a chemical reaction to do that, it's really important that we don't have a lot of excess reactant, because if we paid for that, that's just money that isn't being used. So we can use stoichiometry to figure out the exact amounts of substances that need to be combined in order to make a desired amount of product. So reaction stoichiometry, the definition, it involves the mass relationships between reactants and products in a chemical reaction. So mass relationships, if you start out with a certain number of grams of one thing, how many grams of product will we make? Or if we want to make a certain amount of product, how many grams of the reactants will we need? If you want to bake a bunch of cakes to serve a certain number of people, you're going to have to use the right ingredients that are going to allow you to bake the right number of cakes. You don't want to go buy 2 tons of flour if you're not going to use it all. For stoichiometry, balanced chemical equations are necessary. So we are back to balancing equations. So this is an example of what type of question could be explored with stoichiometry. We have the reaction where we're taking copper metal and putting it into a silver nitrate solution. This is a really cool reaction. Remember, silver crystals grow. We produce silver metal and copper 2 nitrate. So our reactants are copper and silver nitrate. So here's the question. How many grams of silver will be produced if 5 grams of silver nitrate reacts with an excess of copper? So what the question is saying is that it's telling you that this is going to be what limits how much silver we produce by indicating that we're going to have more than enough copper to fully react all of this. So if I have some silver nitrate and I want to figure out how much silver metal is going to be produced, I can use a stoichiometric calculation to solve that. And that's what we're going to be exploring today with this. Before we do that, we have to review a couple of things like unit conversions and molar mass. And I have to teach you about something called a mole-to-mole ratio, because that will prepare us for doing stoichiometric calculations. So, the review of unit conversions. Unit conversions always involve 2 things. And I'm going to refer to whatever's given. So I gotta turn the pen on. Whoops-a-daisy. Whoops-a-daisy. Will it make it blue? Yeah, we'll use blue. Okay. So In unit conversion problems, there's always something that's given, that's associated with a number, and there's always something that you're wanting to find. So I like to refer to whatever is given as the A, the starting point of the problem, and whatever we're trying to find as the B, because we're going from point A to point B. Now in unit conversion problems, you start with A and you end with B. So you always start by writing down what's given. 2357 miles. And give yourself a little room, and over here write down what it is that you're trying to solve for, which is inches. Okay, this kind of gives you a map of where you're starting and where you want to be. Now, unit conversions involves multiplying by conversion factors that are equivalent to 1. Whatever unit you have to start with is going to have to be the unit that is in your denominator. So think about what we know about the mile. So 1 mile equals, I don't know how many inches are in 1 mile, but I do know that 1 mile equals 5,280 feet. Now if I were to stop the problem right now and solve it, I would have unit cancellation because the numerator unit and the denominator unit cancel each other out. I would take 2357 times 5,280 and it would multiply out and I would get my answer in feet. But I don't want my answer in feet. So I need to go for another conversion factor. In this case, since I have feet in the denominator, I have to follow the same trend and put feet there. I know that 1 foot is 12 inches. My feet cancel. And now to get the answer to this, I would just multiply across the top and get my answer. Now I'm not worried about the answer right now. What I want to emphasize is the process with unit conversions. So whenever you have numerator and denominator, the same units cancel, just like, so say I had 2x squared y over xy. You know the y's would cancel. This x would cancel, and one of these x's would cancel, and that would simplify to 2x. Okay? So the same thing. You have the same unit in the top and the bottom. They cancel. Here, the numerator is, the unit is miles. So I purposefully put miles in the denominator for unit cancellation. Okay? So the next one is convert 56 years to seconds. I'm going to do this up here because I feel like I'm running out of room. Well, I can do it. All right, again, crazy things are happening. I am going to solve this up here. So you start by what's given, 56 years. So that is my A, what's given, and I want to convert it to seconds. That's my B. So 56 years, I want to find seconds. And my first conversion factor is going to have years in the denominator. I know that 1 year is 365 days. And my years cancel. Since I have days here, I need days down here. I know that 1 day is 24 hours. Oh, I thought that might erase for me. It didn't. Now my days cancel. I know that 1 hour is 60 minutes. And I'm running out of room. My hours cancel. And 1 minute is 60 seconds. And my minutes cancel. So I could just multiply straight across the top and I would get my answer. Now if there were units on the bottom, we would divide. Okay, so this is a list of what every single stoichiometric calculation includes. And some of what I go through in the list may seem a little foreign to you, but that's okay, because when we're done, I'll go through the list again and it won't seem that foreign to you. First and foremost, all stoichiometric calculations include the use of a balanced chemical equation. Ooh. I don't know if I'm going to write, but I think I might write. Also, so the equation must be balanced. Also, just like with unit conversions, we're always interested in two things: something that's given and something that we want to find information about. Now, it's not just a coincidence that I chose this to be A and this to be B, because I want to use the same consistent way to represent whatever's given, which is associated with the number, with the A, that's your starting point. That's where we start, and B is where we finish. That is what we want to find more information about. Now, a chemical reaction might have three things combining to form two things. It might have 5 different substances involved. But all stoichiometric calculations are only interested in 2 of them. So we have to identify which 2 the problem is asking about. The first is the given is always going to be the one associated with the number, and the wanted is going to be what it asks you for. Oh, it seems that the pen shuts off when I clickety-click the next thing. All right, in stoichiometric calculations, we have 3 conversion factors that are used. Now, I'm just going to warn you, I don't want you to get alarmed. These are going to look a little weird to you because you've never used conversion factors that looked like this. Whoops. This is kind of irritating. I have to activate the pen each time. All right, so one conversion factor has to do with this equality. And this is the conversion factor that will always be used with substance A, or the substance that's given. If you're given that you have a certain number of grams of a substance, we need to have grams of that same substance on the bottom to get unit conversions. So this is the conversion factor. 1 mole of A equals the molar mass of A, and 1 mole of A is on top, the molar mass is on the bottom. We're going to be reviewing molar mass in just a bit. Another conversion factor is also, it also uses molar mass, and 1 mole of B is equivalent to the molar mass of B. Well, 1 mole of any substance is equal to the molar mass of any substance. But in this case, we're talking about whatever we're trying to find information about that wanted. In this case, it's always going to be 1 mole of that substance is equal to the molar mass on top in the numerator. The last type of conversion factor used is a mole-to-mole ratio. The mole-to-mole ratio occurs in every single stoichiometric calculation. All calculations will have this. All of them. If the problem doesn't ask anything about mass, you're not going to use the ones involving mass. But every single one is going to use the mole-to-mole ratio. And I will talk a little bit more in detail about that mole-to-mole ratio in just a little bit. Also, I will talk about molar mass in just a little bit. I can't remember which one of these is on the next slide, so we'll see when we get there. All right, it's a review of the molar mass. Molar mass comes from taking how many atoms of each element are in the compound and adding up the atomic masses. So with carbon dioxide, we have 1 carbon and 2 oxygens. Now, from the periodic table, the mass of 1 carbon is 12.01. The mass of 1 oxygen is 16. Now, since we have 1 carbon and 2 oxygens, in order to get the molar mass, we have to add up 1 carbon, 12.01, and 2 oxygens, 16 plus 16. So when we do that, we get 12.01 plus 2 times 16 is 44.01 grams. This should say grams. So 1 mole carbon dioxide equals 44.01 grams. And then again, those atomic mass numbers come from the periodic table. Okay, talking about the mole ratio. The mole ratio is a conversion factor that relates the amounts in moles of any 2 substances involved in a chemical reaction. And we're going to go through this example here. So we have aluminum oxide, and we're breaking it down into aluminum and oxygen. Just a little review on how to get the correct formula. This is an ionic compound. Oh, geez Louise. This is an ionic compound, so aluminum has a +3 charge. Oxide has a -2 charge. So the correct formula for aluminum oxide is Al2O3. Now, aluminum is just Al. It's not one of the 9 substances that has a little subscript, but oxygen is. The formula of that is O2. Now, this equation is not balanced, so the first thing I have to do, since all stoichiometric calculations involve a balanced chemical equation, is I need to balance it. As I look at this, I notice that I have 3 oxygens here, but only 2 there. So to make my life a little easier, whenever this happens, one thing that I try to do is I say, okay, what happens if I double this? That'll give me an even number at least. So now I have 6 oxygens, and if I put a 3 right here, now I have 6 oxygens on that side. Since this 2 made me have 4 aluminums here, if I put a aluminum there, or a 4 there, it gives me a balanced chemical equation. Okay, these are the coefficients, 2, 4, and 3. Now, from before, I said that a conversion factor looked at, or a mole to mole ratio looked kind of like this. We had moles of B, moles of A, and then I had these blanks here, and I didn't really explain what those blanks meant. These blanks come from the coefficients of the balanced, I don't know, this writing is looking bad again, chemical equation. Maybe if I write smaller or slower, it's better. Okay, so I can compare any of these substances to each other, and I can say for every 2 moles of aluminum oxide that I start with, I will produce 4 moles of aluminum and 3 moles of oxygen. A way I can set that up as a conversion factor is I can say I want to compare moles of oxygen to moles of aluminum. What I do is I take whatever number this is, the coefficient, and I just go ahead and put it right in that spot. So for every 4 moles of aluminum, whoops, I did that wrong, and I can't erase. So I'm going to have to scribble, 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 because the number in front of oxygen is 3. I have 3 moles of oxygen. Okay, let's try a mole to mole ratio between moles of aluminum oxide and moles of aluminum. If I look at the coefficients here, for every 2 moles of aluminum, I have 4 moles of aluminum. Oh, I'm sorry, I made a mistake. Let me say that again. For every 2 moles of aluminum oxide, I have 4 moles of aluminum. Now, I could also, in the same token, put the 2 moles of Al2O3 on the bottom with 4 moles of aluminum on the top. I'm sorry, that looks really terrible. It looks more like a 1 here. I'll make that a 2. Okay, I can set that up either way. It's all going to depend on what substances I'm interested in this particular problem. If I want to find out how much aluminum I will make if I start with a certain number of aluminum oxide, then this would be my A and this would be my B. So once you identify what your A and what your B is, you can set up your mole to mole ratio. In this case, it's always moles of A on the bottom with moles of B on the top. If this is my A, then my moles of aluminum oxide are on the bottom. If this is my B, then my moles of aluminum is on the top. All right, so that's the mole to mole ratio. And again, you might be wondering what this even means. Why does this stuff matter? It's going to make a little more sense when you start to put these concepts in action. And the next segment of the video is going to involve doing stoichiometric calculations for each of the 4 types. And just as an introduction to the next part, one type is called moles to moles. One type is called moles to mass. One type is called mass to moles. And the last is called the mass to mass problem. And typically, a mass to mass problem is the one that's most useful to us. It's most convenient because we measure things in grams, and oftentimes we want to find out how much stuff we can make in grams. So here, if we start with 30 grams of hydrogen fluoride, how many grams of tin fluoride can we make? Okay. Now this is an application that is useful. If I'm the one in charge of making toothpaste and I want to put my tin fluoride in there, and I need to find somebody that carries out this reaction, whoever is carrying out the reaction is going to need to know how much of this to make, and therefore they're going to need to know if you start with a certain amount, how much of this is going to be made. I know that was a little confusing. I stumbled on my words there. I better stop now. So that concludes this introduction to stoichiometry. The next little bit will show you some examples of how to apply the calculations. Thanks for watching.